derivatives on graphs. That is, if you look at the graph of a function, what can you tell me about the derivative of that function? Without looking at any, formulas or anything, just looking at the graph. Thank you. So something like, if I have a graph like this, maybe, what can you say about that graph just by looking at the graph in terms of the derivatives? Remember, the derivative is the slope of the tangent line as you look along the curve. And for example, I can see some places where the slope of the tangent line must be 0. It's hard to just eyeball what the slope is, but you can say fairly easily where is it 0, and you can also say where is it positive versus negative. Positive slope, remember, means the line is going up as you go to the right. Negative means it's going down. And 0 would mean it is straight up horizontal. And I can see 2 points where it's 0. That would be like here is one, where the tangent line, if I were to draw it in, would look like this. And that is a horizontal line, which is to say slope 0. And also the other point I can see is right there, where the slope is 0 at this point also, right? And so these are 2 points. That doesn't look like 0. Flatten it out. Move it up. There we go. All right, so these 2 points, f prime equals 0 here, and also here, right? So it's fairly easy to look and see where it's 0. You can also look and see where it is either positive or negative. Like I said, positive means the line is going up as you go to the right. Come on in. And negative means the line is going down as you go to the right. And so, here's two. Sorry. That wasn't my ding, I don't think. Here's 2 points where it's 0. But in between those 2 points, it's not 0. Like in between here, it's not 0 there. That means it must be either positive or negative. What do you say? Is it positive or negative in between there? Negative is the answer because it's going down as you go to the right, all right? Versus going up as you go to the right, it's positive. So you can say in this region in between, I'm going to write a big old N right there and a big old P up here, meaning it's negative in the middle there, but positive on the right side over there. In fact, I put a big P over here because here it's positive and quite steep. Actually, back here, it's always positive along this part, but it's not so steep like around here. It's still positive, like it's still going up, but it's not very steep. So maybe I'll indicate that with some it's like a little P getting gradually bigger until this master P over there, if you will. Remember that guy? All right. So these are all positive along here, not very positive, and then increasingly more and more positive, okay? And in the middle, actually, you can see it's fairly steep in the middle here, but not very steep around here, and also not very steep around here. So it's more like here is sort of only slightly negative near those points, but more sort of quite negative in the middle. And then I could do the similar thing over here. What about this one? Is this one positive or negative for the slope? Show me the thumbs. I see most of the thumbs are up. The answer is thumbs up. This one is positive. Remember what that means is going up as you move to the right versus going down as you move to the right. You may be, don't be fooled by this little arrow here, which is going down. So you might say, oh, well, it's going down, so it's negative. But when we judge this up versus down, it's always about as I'm moving from left to right, this is going up or down. Yeah.
Are the points that are 0, 0 because there's no change in positive or negative?
You could say that, like right here, it's not going up or down. Okay. So it must be 0. Yeah, I would say more technically, it's because this tangent line, its slope is 0, because the rise over run thing equals 0. Okay. So anyway, over here, it's also positive, and I would say very positive back there, and not, only slightly positive, like right around here, but still positive. All right, these are the derivatives as we go along the picture. Actually, what we've said here is enough. We can, in fact, draw the graph of the derivative. And this is what I want to talk about sort of for the rest of this little section here, and then we'll go on to something else. Draw the graph of the derivative. So the idea on a problem like this, you're going to have some homework problems like this, and you should expect to do this on the test. I show you the graph of one function, like I did, and then your job is to draw a graph of the derivative. Now, your graph isn't going to be exact, but you can actually be fairly precise about it. So it's easiest if you draw your answer directly below the first one, because I'm going to use the fact that I can sort of line stuff up to make this a little easier on myself. So I'm going to try and put this all on the screen at once. All right. And now, what I draw down here is supposed to represent the derivative of what you see up there. And what that means is when this one, for instance, right here, the derivative is 0, which means what I'm drawing down here should equal 0. That is to say, its y value should equal 0 at this point. So I'm going to try and sort of line up this point. If you try to draw these next to each other, side by side, it's much harder. So I would suggest you leave yourself some room on your paper and just put it directly below so that you can line these points up. These 2 points both represent places where the derivative equals 0. And since this graph, what I'm about to draw, the y values are determined by f prime. That means when the derivative is 0 here, I'm going to draw it as a y equals 0 point down here. All right? So this is going to be some kind of curve that I'm about to draw, which goes through these 2 points. The question is, like, what does it do in between? I want to try and sort of connect the dots. Think about what the curve ought to do. Your choices, I suppose, are it could do something like that, or it could do something like that, right? Because it has to connect the 2 dots, and it's not going to be 0 any other place in between, because we already said, you can already tell these are the only 2 places where it's 0. So it has to either go up and then come back down to this point, or go down and then come back up to this point. Which one is it? How you know which one it is based on looking up here at the positive versus negative kind of thing here, all right? I said that throughout this region, the derivative is always negative. That means what I draw down here should be on the negative side of the x-axis. It should be down here, because what I'm trying to draw is supposed to be negative. And so it's not that one, it is this one. So I'm going to try and write some commentary here. F prime is negative here. So that means the curve's y values should be negative, which is why I drew it downstairs, down under the x-axis, rather than up here. Those would be positive y values. I drew it down here, negative y values. All right. And the reason it's this one down here is because up here we said it was negative. The slopes are negative in this region. So I wrote down there. All right. What about on the right here? From this point, the line must continue to the right. It either goes up like this or it turns around and goes down. Any ideas? Your answer should be based on whether it's positive or negative up here. Should we go up or down? I say up. It should go up, because this says in this region the slopes must be positive, which means what I draw down here should be upstairs rather than downstairs. It should be on the positive side of this picture. So it's not that one, it's this one up here. It goes up, positive, all right? And what about on the far side? This is the end of it, right? So this, similarly, this curve is either going to go up here or down here. This says positive, which means I have to draw something down here with positive y values. That means it must be up here. And so it looks like that. So the answer here looks kind of like a parabola. All right. I put this one up here because the derivative is supposed to be positive in this area. That's why I drew it on the positive y value side of this picture. All right. This can be slightly confusing because you might think to yourself, what isn't this line going down? This one that I drew is actually decreasing here. This line is going down, but it's supposed to be positive. It's because positive here means that this line is going up, but what I'm graphing down here are the actual values of f prime, and in this region, those values should be positive, which means the y values I'm using here have to be positive. It's got to be up here, not down there. All right. This can be a little bit tricky. I don't know if this seems hard when I do it. It can be a little tricky, but it's not so bad. I got one more example, and then I got one for you all to try. Any questions at this point? Let's try one more. All right, give yourself some room. Oops. I am again going to draw two pictures here. How about like that? This is my original function f of x, and your job is to draw the derivative, f prime of x. So I want to try and do this in the same way. My very basic strategy last time was draw the dots to get it started and then connect the dots in the appropriate way. So I want to do the same thing here. I begin with the dots, which are where the derivative equals 0. So where are the zeros? In this picture, actually, I'm looking for places where the tangent line goes flat. I can see 3 such places on this picture. I hope that you can see them too. There's one here at the top of the hill. There's one here at the bottom of that thing. And then I see also, it looks like one around there somewhere where the slope goes flat. All right. Okay, so those 3 points become dots that sit on the x-axis in my answer, and they should sort of line up here. So I'm trying to line this one up there. Oh, maybe I'm gonna do my fancy dotted line. Oh, how do you like that? And here, yeah. This is what they pay me for. Okay, so there's a dot here and a dot here. All right. These are my 3 dots, and I'm going to try to sort of connect the dots with curves that go on the appropriate side, either above or below the x-axis. And if you like, you can sort of draw in your original curve positives and negatives. Anybody want to say for the leftmost part here? Is this a P or an N? It's positive, yeah. You should look from left to right. Is it going up or down? And this leftmost section is going up as you move from left to right. So this is positive over here. The next one is going down as you move left to right. So that's a negative. The next one is going up as you move left to right. That's another positive. And then the final one, as you move left to right, is also going up. So this one is also a positive. All right? You may ask yourself, do these always alternate, positive, then negative, then positive? No. Like the last one, you can see 2 P's in a row. All right. And so when I draw my curve downstairs, what's it going to be? Over here, this positive region means I should be drawing this curve in a way which is always positive y values. That is always above the x-axis. So it needs to be up here and come down to this point, up here. Positive refers on this picture, positive refers to where are the y values? Are they up above the x-axis or down below the x-axis? On this original picture, positive, negative refers to the slopes. All right, how about in the middle here? This being a negative, it means my curve in this region needs to go down here rather than up here, because the derivative is supposed to be negative in that region. Next is a P. That means the curve goes on the positive side, that is up above the x-axis rather than below. So that looks like that. And then finally we have another P. This is a little weird, but it means the curve actually goes back up at the end. It doesn't come down. It goes back up. So it's something like that. This is a graph of f prime of x. Yes?
We have either an ending or beginning to the graph on top where x is equal to 0 and it just kind of goes straight off.
0, yeah.
So
You mean like a flat horizontal line forever?
Yeah.
Uh-huh.
What would we put if that were to happen?
Yeah, this is possible. This I would say is a little strange. No offense. It would, something like that, I guess you're suggesting. All 0 slope there. So I would draw this one, I would say, looks like, well, there's a 0 here. And then there's a 0 here, which kind of like stays 0 forever. So the curve, that's a negative followed by positive. It would look something like this. And then the curve would just sit at 0 for the rest of time that way. Yeah. This I consider fairly strange, and you shouldn't expect to see something like that on the test, but it's a good question. I like strange questions. All right. Excellent. So let's try another one like this. I will draw the picture of f of x, and your job is to draw a picture of the derivative. This, I believe, is number 8 on the list. Graphs of derivatives. Derivatives on graphs, something like that. Sorry. Like so. All right, see what you think. I will give you a few moments. I'll come around and see how you're doing. I would suggest you start with the dots and then try and connect the dots. Oh, you know what? This is the one I just did, isn't it?
Yeah.
Sorry, I just copied the wrong picture. I hope you got that one again. Can you not do that though? Sorry about that. I wasn't paying attention to my notes. Such a good example. I got another one. This one's even better. How about that? Smooth that out a little. All right, this is going to be great.
There's one more. I meant for there to be just one there. So what is that line? This one here?
Yeah.
Okay. So I think in between these two, it should be.
All right, let's talk about this. I see most people did great. This, you know, if you like sort of geometric type things, you might feel like this is a lot easier than other stuff, which is based on more, you know, formulas for everything. Okay, so I have 3 interesting points. Sorry, I'm off the top. There, and there, right? These give me 3 points down here, here. And on the left side, as far as positives versus negatives, this is positive here because it's going up as you move left to right, then negative again, and then positive. So I want to see positive on the left side means up above the x-axis, and then negative for the next region means it goes down below, and then negative again for the next region means it goes down again, and then positive like so. There you go. I hope you got something like that. All right. I didn't intend when I made up this example for it to look so shapely and suggestive, but that's what it is. PG-13 example. All right. Any thoughts about that or questions? Keep your thoughts to yourself. All right. Let's do. I got one more. These really, they don't get any more complicated than that. There is one more kind of situation that we should discuss, and that is, what if there's a vertical asymptote? This can cause a little something to happen. It's not so complicated though, so we can talk about it. A vertical asymptote, or perhaps more than one, you can handle it just fine. A vertical asymptote, so I mean, here's an example. Everybody knows what I mean by a vertical asymptote, I think. But a vertical asymptote is, get my dotted line on, one of these things like this, and then the curve goes, let's say like that, and like that. All right, here's one with a vertical asymptote. Before getting too upset about the asymptote, we can still start off by finding the points where the derivatives are 0 and indicating positives versus negatives. Now, in this case, there is only one such point. It's right there. That's a point where the slope is 0. I don't see 0 anywhere else. What about positives and negatives? I see over here is positive. It's going up as you move to the right. After that dot, it becomes negative, going down as you move to the right. And then after the asymptote, it is again negative. All of this stuff over here is moving down as you go to the right. So it's like so. But I will have you notice that the slopes here, as you approach the asymptote, like right here, the slopes are negative, but they are basically becoming vertical there, right? And a vertical slope is kind of like slope infinity. We don't typically talk about vertical slope because that the rise over the run, it's like the rise is infinite. So anyway, what I'm saying is near this point here, the slopes are becoming infinite. And also near this point here, the slopes are becoming infinite. What that means is when I draw my picture down here, my picture of the slopes will also have a vertical asymptote in the same place. And so this is sort of the basic observation that lets you do these kinds of problems. A vertical tote in f of x makes a vertical tote in f prime of x at the same spot. All right, so the picture that I'm about to draw in my answer will also have a vertical asymptote at the same location. And then that, once you know that, you pretty much do everything else as before. So I'm going to try and scroll up here. I can begin by putting my single point where it goes, which is right there. I'm trying to line it up as usual. And then I'm also going to put an asymptote in the same position. So we have a vertical asymptote here in the same place, lining up with the one from before. All right. A vertical asymptote in the original picture creates a vertical asymptote in your answer in the same location. Other than that, you just sort of do everything as you usually do. Just when you draw the curves in your answer, your curves must respect the asymptote. That is to say, when you draw your curve, you don't make it run straight through the asymptote. It has to either go up forever or down forever to approach the asymptote. But we'll get there when we get there. Let's just draw the curve starting on the left side. We begin with positive, which means when I draw it down here, it has to be up here rather than down there. So we start with that. And then the next region is negative. So that means from this dot, I should go down. It has to be on the bottom side below the x-axis. And because of this asymptote, I should go down, not sort of through the asymptote. It should actually go down forever, approaching the asymptote. So it needs to do that kind of thing. Down, approaching the asymptote. And then on the far side of the asymptote, over here, what is the graph? Here, this is a little strange, but this is always negative. Never zero, never positive. That means what I draw down here must always stay down here. Never crosses the x-axis. Always negative. And you can see actually on the picture here, if you want to think about the sizes or how steep it is, I would say it's not very steep in the middle, but super steep here and here, right? Because the curve is approaching the asymptote here, so it's becoming basically vertical, and also down here becoming increasingly steep. So what I want to see is very negative, followed by not so negative, followed by very negative. What that means is like way down here is very negative, and then not so negative, and then very negative again. So it looks something like that. Approaching the asymptote, of course, in the middle there. I said very negative, followed by not so negative, followed by, again, very negative. All right. Any thoughts about that? Yes?
Do you mind re-explaining the far right part?
Yeah, that's a little difficult because there's no single point to start with over here. You just have to sort of draw it out of nowhere. The fact that this is always negative is why it's all down here, never crossing the x-axis. Why is it down and then up a little bit and then down again? It's because the slopes here are super steep right there, not so steep in the middle, super steep again over here, which means it has to be super negative, then not so negative, then super negative again. Like so. All right, I got one of these for you, and then we'll move on to something completely different. Let's try one with an asymptote. Not the same one. There it is. like that. See what you think.
Find the dots first, places where it's suggest. Positive with that. Well, right that would mean keep it on so when you draw
Yeah, that's oh, that's after this should just be
yeah, it's like it should be approaching the it's like you just
It's not really this.
okay, yeah, all right. Also, it's like yeah, that's good. Yeah.
Do all of that together, except appreciation, and it's like towards mindset, and that's like a negative. Whenever it is a negative. What if it's not a negative? What I did.
All right, let's talk about these. I saw some good ones. So you should start by finding the 0 points. That's here, here, and here. I see 3 of them. So that's here, here, and here. We have the asymptote in the same place. And then I have, as for my signs, negative, positive, negative. This is positive and negative. So my curve goes, we begin with negative, so down here, and then positive, like so, and then negative here, approaching the asymptote like that. I hope I'm doing all right so far. And then positive followed by negative. So positive means I have to draw it up here, and it also needs to respect this asymptote. The only way to make that work is like this. Approaching the asymptote, but it has to be up top, all right? And then to the right of that, it should be negative, so it should just go down, like so. I hope that's what you got. Any questions about those? These can be a little bit tricky. I mean, I suppose it depends if you're the kind of person who would rather like work with equations all day long or draw pictures. Some people are comforted by the equations. Yes?
So for the right side, do we need a curve in the top part towards the asymptote, or do we just draw like a straight diagonal line?
It should not be a straight line because a straight line would eventually go through the asymptote, which is not allowed. Yeah, so it really does need to curve. Yeah. Yeah, in general, I don't care if your pictures are, beautiful looking, but they have to be minimally accurate. All right, excellent. Great, we got plenty of time left to start up the next section. The next section is something that I know some of you are eagerly awaiting. It is a fact that I've been mostly keeping to myself so far, that there are very fancy tricks for finding the derivative of certain functions. Tricks for the derivative. These tricks will allow you to avoid using this formula, lim h goes to 0, f of x plus h minus f of x over h. If you ask me, this is something worthy of tricks to avoid, because this is a real pain to use. You learned that when you did the homework this week. There were only 5 questions, but each one of them involved one of these, and they take you several minutes to work out, and you probably mess it up while you're doing it. So in some situations, and in fact many situations, there are very simple tricks which can allow you to sidestep this formula and get the same answer more or less immediately. You can do an entire derivative or instantaneous rate of change problem basically in your head without thinking at all. For example, because I'm some sort of super genius, I happen to know, here's an example, the derivative of f of x equals 5x squared minus 7x plus 2 is, anybody know the tricks? I know some of you have seen the tricks before. You don't want to shout it out, impress your friends? Nobody wants to impress their friends. 10x minus 7 is this particular answer. You can, once you know the tricks, so by the time we leave today, you will be able to just immediately shout out the answer here, while your idiot friends spend 15 minutes going through the thing with this formula. The tricks are really much more convenient. Around this time, you may be wondering to yourself, why did he make us do that whole thing like that before if there were such awesome tricks to be had? And my answer is somehow that it is important to understand what the derivative is all about, and really it is about this formula. There are tricks for doing it faster, but us as college students learning about calculus, you should really know how to use this formula. It's kind of like if a little kid asked me, why should I ever learn how to add numbers if I can do it on a calculator? I would say, like, well, yeah, you can do it on a calculator, and to be honest, like when you're a grown-up, you will do it on a calculator, but it's still important, like in general, that you understand what that's all about. So it is important. There will be a test question in which I ask you to do this, but this is not the kind of thing that we're going to be doing all semester long because of these awesome tricks. Questions like this are actually much easier than they might have seemed before. So there will be a little bit of a journey to get there, but it involves tricks for finding derivatives specifically of powers of x. That's the real deal. And then there's some simple tricks for combining them together into any sort of polynomial like that. But let me just say some notation first of all. We write, like in that example that I just wrote there, sometimes it's a pain to have to write this like separately. Here is f of x, and here's f prime of x, the derivative. It's a little nicer in some cases to use a notation like this. So this says d over dx. This looks like a fraction, but it's not actually a fraction. This is just the way that we write the derivative as an operation. So this right here means when you see this, you say the derivative of. If you want to write the derivative as an operation, where you plug a function into it and you get another function out as the answer, it's written in this way, d over dx. The derivative of this function equals this function, all right? That's just a simple way of writing the derivative of something. We have already, I said before, I want to talk specifically about powers of x. And actually we have already done several examples of derivative of powers of x. Last time, or maybe the time before, so we've done the derivative of x squared. I think this was like one of the first examples that we did using that definition with the limit of whatever. And the answer, I don't know if you recall, was 2x in that case. Yeah?
Don't you just multiply the exponent to the
Yes, this is the, something like that is the trick. She says, don't you just like move this 2 down here and you get 2 times x? That certainly is what happened in this example. Now, I want to talk about some slightly more complicated situations and see if that basic rule is what applies. So can we just do one last time with the limit definition? What about x cubed? I want to see what happens in there and then see if we can sort of deduce some kind of pattern here. So the derivative of x cubed. If I do it the old-fashioned way, and this is the last time we're going to do one like this, because like I said, the sweet tricks are so sweet that you never want to go back after doing it with the tricks. Using this function here, one last time, using the definition of the derivative, it says f of x plus h minus f of x divided by h. And this we plug in to the function first step. So where it says, everybody's used to this by now, where it says f of x plus h, it means I do f of x, which is here, but I replace x by x plus h. So it looks like x plus h cubed. And then minus f of x is just x cubed. All this divided by h. And now what happens next is we have to expand this x plus h, the whole thing cubed. And this is actually a particularly nasty version of the FOIL thing. So it needs to be x plus h, x plus h, x plus h. There was one like this on the homework. Divided by h. And then you have to multiply that out. And this is the worst step here. It involves doing the FOIL on 2 of them first. And then whatever that answer is, you do the FOIL again with that and the next one. I hope you don't mind if I'm going to skip those steps. There's actually another trick for doing things like this, which we don't need to get into, because this is the only time we're going to do this. But what you get in this case is x cubed plus 3x squared h plus 3xh squared plus h cubed. This is a little life hack that I'm aware of that lets you quickly compute these kinds of big FOILs. It involves Pascal's triangle, if you ever heard of that. It's not important for the rest of the course. But anyway, that was just the first part there. X plus h times x plus h times x plus h. Then I see minus x cubed, like so, all over h. And now we can cancel stuff out. I have x cubed at the beginning, minus x cubed at the end. Everything else has to stay. What remains is 3x squared h plus 3xh squared plus h cubed all over h. And we finish, as usual, by factoring h out of everything on the top. It's h upstairs, and then what's left over is 3x squared plus 3xh plus h squared divided by h. Cancel the h's. And finally, we plug in h equals 0 to finish. It says 3x squared plus 3x times 0 plus 0 squared. This is 3x squared. That's what we were looking for. All right. That is probably the last time we're going to actually use the definition of the derivative in class. So what I was trying to make a comparison with this one here, right? So maybe I will write just to summarize here, the derivative of x squared is 2x. The derivative of x cubed is 3x squared. All right? And there is a pattern here. If I were to write this in general, can I say derivative of x to the power n? Generally speaking, it is what she said before. The exponent here, like this 3, becomes the new coefficient. And how do you determine the exponent here, the new exponent? See the pattern of that? Yeah, you minus it by 1, he said. You decrease the power by 1. And that's the new exponent. So if I were to write this as a formula, it looks like x to the n, when you take the derivative, becomes n times x to the power n minus 1. The old exponent becomes the coefficient, and the new exponent is just the original one reduced by 1. So this is a super important formula which you should memorize, definitely. Although this is the kind of thing that we're going to be doing this so often, like, 20 times a day from now on, that you're not going to have to sit down and memorize this. But this is referred to as the power rule. This is the rule for taking the derivative of a power of x. That's why it's called the power rule. All right. There is one special case of the power rule which is important. It looks slightly different, but one special case would be when the I'll just write it. What is the derivative of just x by itself with no power? Now, I want to try and somehow fit it into this formula here, but there's no exponent written. There really is an exponent here. It's just not written. What is the exponent really? It is 1. Yes, I see some fingers. So the true exponent is 1 here. So I'm going to use this formula in the case when n is 1. What do I get? I get 1 for the n, 1 times x to the power n minus 1. The n is 1, so this is now x to the power 0. And what is x to the power 0? Anybody remember your high school? I don't know. Anything to the 0 power
Is it 1?
is 1. Yeah, anything to the power of 0 is always equal to 1. So this actually is just 1. All right. So this, if you like, I mean, really, it is just a somewhat weird example of the power rule again, but you might want to, I would say, just memorize that one as a special case. The derivative of x by itself is just 1. So any power of x, you can use this power rule. If it happens to be x to the power 1, you use this rule right here. All right? And then there's one more sort of special one. I would like eventually to talk about any polynomial. And a polynomial is based on powers of x added together and also individual constants. So we should talk about, this is the derivative of any power of x. What about the derivative of an individual constant? What about derivative of something like, 12, just a number? What is that derivative? There's also a rule for this, which you should just remember. This rule, you could derive this fairly easily using the definition with the limit and see what you get if I use 12 for my function. It's a little easier to just think about this in terms of the graph. What is the graph of f of x equals 12 or y equals 12? Does anyone know what the graph of that looks like? Just a graph of a constant?
Horizontal line.
Yeah, it looks like a horizontal line, and in fact, in this example, it would be the horizontal line at y equals 12. Anybody want to tell me what is the slope of that line? If I ask you what's the derivative of this thing, that's about the slope. It is
0.
0. Yeah, 0. Actually, it's 0 everywhere. No matter which x value you're talking about, the slope is always 0. That means this derivative is 0. So this is one last rule to put in a box. Maybe I'll put them all together here. Derivative of x to the n is n x to the n minus 1. Derivative of just x by itself is 1. And the derivative of any constant c is 0. So these are the basis of all of the tricks that we are going to use when dealing with simple, well, polynomials mostly. All right? And I would like to point out that this one here is even better than it seems. Actually, this one works for any n, even negatives and fractions. Exclamation, this is good news. It works for any n, even negative numbers and even fractions or decimals. All right, so we could do, just very simple examples. What's the derivative of x to the 12? The answer is 12x to the 11. You put the exponent as a coefficient, and then you decrease the old exponent by 1. Or I could do something like, what's the derivative of x to the negative 3? It's negative, but what I said is you can use the exact same formula even if the exponent is negative. So I bring the negative 3 down, it becomes a coefficient, minus 3 times x. Here's a little tricky trick. It's not much of a trick, but what's the new exponent going to be? I had negative 3, I decrease it by 1, and we get negative 4. Yes, don't say negative 2. Negative 3 minus 1, it decreases to negative 4. All right? This is how we subtract a negative number, minus 1. And you can even do fractions. For example, fractions or decimals. If I had, for some reason, x to the power 1.75, the derivative would be 1.75 x to the 0.75. I subtracted 1 from the exponent, right? Or if I had something like x to the, 3/8, the derivative of x to the 3/8 is, don't think too hard about this, 3/8 times x, and what should the exponent be? Maybe you do have to think a little bit about this. 3/8 minus 1, whatever that is. Maybe I'll just write 3/8 minus 1. What is 3/8 minus 1? 1 is 8/8. So 3/8 minus 8/8 is negative 5/8. So this is a little annoying to deal with the exponents sometimes if they're weird numbers. But you always just subtract 1 from the exponent. Okay? Yes?
Are we likely to have like fractions and decimals on the exam?
Like that, maybe.
Okay.
I hope you can subtract 1.75 minus
Well,
1.
yeah.
But not more complicated.
Okay.
Yeah. In this context, all you need to do is subtract 1. So, yeah, you can handle that. Yeah. Okay, a few more things to say. You may notice these are not polynomials. These are what we call monomials. That is like a polynomial, but just one thing. How do you handle a bigger thing? It's not so difficult. There's 2 more rules to know. We got plenty of time to talk about 2 more rules. So these have to do with, what if you have some of these things but they're added together? That's how you would make a real polynomial out of these, is by adding them up. And also by inserting more coefficients. So what if we have a constant in front? So what about multiplying by a constant? There's a special rule for that. Again, this rule is something that is actually easy to show using the limit definition of the derivative. I don't think we need to go through the details, but basically if you write the limit definition of a derivative out, you get some fraction with the numerators are f of x plus h minus f of x. If you have constants multiplied onto them, that constant can factor out of the entire fraction. And in fact, you will see that you can just factor the k out of everything. All right. This is yet another rule, which this one I would say even more so than the others. You're not really going to have to memorize this because you're going to do this just sort of instinctively in all of the examples that we talked about. But it says if you have a constant and you're taking the derivative, this constant will stay like it is, and then you just multiply by the derivative of the rest of it. So how you would use this in a typical example is, what if I ask you what's the derivative of 3x to the 5? using what I said in the box, you can factor the 3 out through the derivative. So this is the same as 3 times the derivative of x to the 5. And what is the derivative of x to the 5? That we already talked about. You do the thing with the power. You move the 5 down front. So the 3 stays like it is out there. And then I go 5x to the 4, right? And then my final answer, if you want to multiply, 3 times 5 is 15, x to the 4. That's the answer. So we use the thing in the box that's the justification for why we can just kind of push the 3 out here and leave it out here, do the derivative there, and then recombine them at the end. All right? Now this actually, all of this, you probably are not even going to think it through in this way. The way that you would typically think through this whole thing, I would expect you to just jump from here all the way to the answer. And the way to sort of imagine this, I think it's worthwhile to imagine what you do is this exponent moves into the front as usual, and what happens when the 5 kind of meets the 3? It multiplies onto the front. All right, so the 5 multiplies onto the 3 as the coefficient, and it becomes 15 out front, and then you get x to the 4 because you decrease the power by 1. So the way to sort of think this through is the exponent multiplies onto the coefficient. And then, as usual, you decrease the exponent by 1. All right? This is the way that I wouldn't actually memorize these as formulas. I would sort of remember this little slogan here. You move the exponent down into the front and multiply it onto the coefficient and then decrease the exponent by 1. All right. So, for example, we can do some, fancier ones. I could do the derivative of 8x to the 5. What's that going to be? Somebody want to shout it out? Do what I said. You multiply the exponent onto the coefficient and then decrease the exponent by 1. What do you get? 40x to the 4th. I agree. Yeah. That's all there is to it. How about, here's a slightly fancier one, 5x to the minus 7. Not much fancier. Yeah. Negative 35x to the minus 8. Great. Negative 7 times 5 is negative 35, and then you decrease the power by 1. Minus 7 becomes minus 8. That's how we do it. All right? These can be, it doesn't really get much more interesting than that, but sometimes these can get a little cute. For example, what is the derivative of square root of x? Now, on its surface, this looks completely different from everything that I've been talking about, but actually, you may recall from your youth that you can rewrite the square root in terms of some kind of power of something. Anybody remember this? It is x to the 1/2. So the square root of x, remember, root x is the same as x to the 1/2. And so this, I can just write like that. I didn't do the derivative yet. That's why I still wrote derivative right there. All I did was just rewriting this in a more convenient form. And now I'm going to do the derivative, which is you move the exponent down front. So this is my actual answer, 1/2 x. And then what's the new exponent going to be? It should be 1/2 minus 1, which is negative 1/2. Yeah, 1/2 minus 1 is negative 1/2. This is a little, I don't know, is that confusing? You may ask yourself, why did I make the exponent negative? Aren't you supposed to subtract 1? And the answer is yes, I subtracted 1 because coincidentally 1/2 minus 1 equals negative 1/2. All right? So this thing about square roots, actually we are going to be encountering the square root fairly often in this class. You should always rewrite the square root as a 1/2 power. There is essentially no time in this class where it's useful to write it as a square root. Your first step should usually be to rewrite a square root as a 1/2 power. Here's one more simple trick that can come up in these, and that would be if it was something like 5 divided by x to the 4. Now this is another thing that we haven't, this doesn't look anything like what I've talked about so far, and you may be tempted, but you should not, going to write this in red, meaning do not say it's 5 over 4x cubed. Can you just like do that usual thing inside the denominator? The answer is no, you can't. There is not a rule for that. That rule about the n times x to the n minus 1, that only works in this very specific situation. It does not work when that thing is inside of another thing or in the denominator or anything. We are going to have to rewrite this in some way just using a power of x. Anybody, there's another trick that you can do with something like this. Anyone recall? How can I rewrite this? Make the exponent negative and move it up into the numerator. I agree. So this step right here is not, I didn't do the derivative yet, which is why I'm still writing this d dx. All I did was I wrote that in a different way. I hope you all remember that a negative exponent indicates that thing is inside the denominator. So if you see a power of x in the denominator, you can always move it up and make the exponent negative. But anyway, now this is in a format that we like for taking the derivative. I get negative 20x to the minus 5, like so. Multiply 5 times minus 4 and then decrease the exponent. All right? In our remaining 10 minutes, I got one more simple rule. So these still, I am only talking about monomials. That is one thing, not a bunch of things added up, which is what a polynomial is. So the last thing I need to discuss is what do you do if you have a derivative of two things added together? There's one last rule for handling a derivative of two things added together. And actually, this rule is so simple that you don't usually even think about it when you're doing it. But here's what the rule is. You just do the derivative of each one separately. Again, this is something that you can prove using the old limit formula for the derivative. But I don't think we need to get into the details. It says if you have things added together, the derivative is equal to, you just do each of the two things separately and add the two derivatives together. All right? So that means I can do examples like derivative of 6x cubed plus 8x squared minus 7x plus 3. This is a bunch of stuff added together, but what the thing in the box means is when you see stuff added together, you just do each derivative separately and add the answers all together. So what this means is I can just do each one, right? It's a bunch of stuff added together. One of them subtracted, but that doesn't matter. 6x cubed, I go 18x squared, right? We multiply the exponent times the coefficient and then decrease it by 1. Then plus 8x squared becomes 16x. Then minus 7x. The minus 7 will stay like it is. Anyone remember what happens to x when you take the derivative? This was a special rule. I see somebody give me the Jonah Hill. It becomes 1, which is to say it sort of disappears from the formula, right? The derivative of x is 1, so this becomes 7 times 1, which is 7. And then the 3, constant, remember the derivative of a constant is 0. I saw that someone was giving me the hand signal. Plus 0 if you like, or you can just leave that part out, all right? And now, as promised, I hope you agree, this kind of a thing is very, very easy to do, right? Like here is, this was one of the ones on the homework. The last one looked like this, 80 minus 5p squared. Your job was to find n prime of 3, I think. Yeah, it was 3. This was the last problem on the homework from last week. I remember it well because I looked at 60 of them. All your answers. How can we do this the easy way? The easy way is we find the derivative n prime of p. What is it? We do the same old thing. What happens to the 80? 80 being a constant becomes 0, so that's a 0. Minus 5p squared, what does that turn into? Somebody want it? 10p, yeah. The exponent, the 2 comes down, multiplies on the 5. Should be negative 10p because we had a minus sign there from before. All right. So this, of course, is just minus 10p. And now your job in this problem on the homework was specifically find n prime of 3. So n prime of p is negative 10p. So n prime of 3 is negative 10 times 3, which is negative 30. And that was the answer in the homework problem. All right. Now, it took me a couple minutes to explain that, but if you know what you're doing, you can do this in, I would say, under 10 seconds probably. Far, far easier than the using the limit definition. So let me just say something about like terminology and how I would expect you to do these things on the test. For example, I will say always do the derivative using these tricks, unless I'll say derivative, sorry, can I squeeze this in, or instantaneous rate of change. Those are the same thing. You should, when you see a question in general in this course about the derivative or the instantaneous rate of change, you should always do it in this way with these tricks, except, or unless I say use the definition of the derivative. That means if I say use the definition of the derivative, that means you do the limit as h goes to 0, that whole thing, which is, in my opinion, much harder. And we are almost never going to do that. I will ask you to do that once on the test, but you should expect that to be it, basically, for the definition of the derivative. All right, and I think that's all I wanted to say for today.